In this video, we'll talk about what L'Hopital's rule is. So I want to begin by recalling our indeterminate forms. So indeterminate forms we saw when we talked about limits. So the examples were 0 over 0, infinity over infinity, and when I write infinity over infinity, either of these infinities could be negative infinity, infinity minus infinity, there's 0 times infinity. Okay, so up until now we had seen these four. These are all examples of indeterminate forms. When I see this form, I can't determine, I don't know what the answer is going to be just by looking at it. And the way we had done these up until now was to simplify our expression. Okay, and I'm going to give some new ones. So some new ones are going to be 1 to the infinity, 0 to the 0, 0 to the 0, and infinity to the 0. Okay, so these are now new ones. Okay, and I want to briefly explain why one of these new ones is indeterminate, but they can all be justified in a similar way. So for example, 1 to the infinity, this is indeterminate, since when I see the 1 to the infinity, this actually means we have a number that's really close to 1. So there's a number that's close to 1, because we're going to be taking a limit. Okay, and then the exponent is getting huge. So the exponent is a huge number. So there's sort of two conflicting things that happen when I have a number that's close to 1 as the base, and then a huge number in the exponent. This is indeterminate because I have something of this form, and we know that in general, if I had 1 as the base and the exponent was anything, 1 to the x, this is 1. Whereas if I had a different number as the base and I let the exponent go to infinity, this would be infinity as long as that base is bigger than 1. Okay, so there's sort of two conflicting things. The base is saying, because I'm getting close to 1, the whole thing should probably be getting close to 1. And the exponent is saying, okay, as long as the base is bigger than 1, the whole thing should be going to infinity. So the 1 and the infinity, they sort of have this tug of war. All right, so I mentioned that back in section 2.3. In section 2.3, we evaluated indeterminate form limits by simplifying our expression. Usually we got something to cancel that ultimately let us plug in. But what if it's either hard or impossible to simplify our function? Hard or impossible to simplify. And for the most part, we haven't seen limits like this because we just didn't know how to handle them, so we didn't try them. But let me give an example. So one example is if I had the limit as theta goes to 0 of sine of theta over theta. So we learned how to do this, and the proof of why this limit ended up being 1, I think it took us like a 20-minute video or something to show that. It involved a geometric argument, it involved some squeeze theorem, but we sort of did it in a roundabout way rather than being able to simplify it. Okay, so in today's section, we'll learn a shortcut for doing limits like this. Okay, this is called L'Hopital's rule. So the preliminary part to the L'Hopital's rule statement says that I'm going to suppose that f and g are differentiable, so they got to be smooth functions, and g prime of x is not going to be equal to 0 on an open interval I that contains a, except possibly at a. Okay, so what we're going to be looking at is if we have a limit as x approaches a of a fractional function. So there's some function f of x on top, some function g of x on the bottom. So if this limit has the form 0 over 0 or plus or minus infinity over plus or minus infinity, then we are going to get to use the following. the limit as x approaches a of our function f of x over g of x. It turns out that this equals the limit as x approaches a, and what I can just do is take the derivative of the top and take the derivative of the bottom individually. So it's not quotient rule, it's just derivative of the top divided by derivative of the bottom. So f prime of x over g prime of x. And I can do this as long as the limit on the right-hand side, so that's this limit with the derivative on top and on the bottom, exists or is plus or minus infinity. Okay, so let's look at some examples. Okay, so I want to start off with that example that I gave. The limit as theta goes to 0 of sine theta over theta. So the first thing that I'm going to do is just see what happens when I plug in. And if I plug 0 into this, I'll get 0 on the top and 0 on the bottom. And this has one of the forms I can use L'Hopital's on, is 0 over 0. So we are going to try L'Hopital's rule. I'll abbreviate L'Hopital's by just writing LH. So you'll see me do that all the time. Okay, so now this is going to be equal to, and the way I'm going to indicate, usually when I do a problem that I'm doing L'Hopital's, is above the equal sign, I'm going to write LH to indicate, oh, that's the step where I did L'Hopital's rule on. Okay, so this is the limit as theta goes to 0, and the rule says, you'll still have this fraction, but now take the derivative of the top function divided by the derivative of the bottom. And the top function's derivative is cosine theta, and the bottom function's derivative is just 1. And now let's try plugging in. So I'll get cosine of 0 over 1, but that's just 1 divided by 1, which is 1. And that's what we know this limit is supposed to be. But this was so much shorter than how we first got the result. Okay, so I'm not going to give a proof of L'Hopital's rule. I want to focus our time more on applying the rule. So I'm going to focus on doing examples. All right, let's look at another example. So in example 2, we have the limit as x goes to infinity of the quantity ln of x being squared over e to the 2x minus 1. So if I plug in as a first step, we will get, well, ln of infinity is infinity, so I'll get infinity squared, which is infinity. And on the bottom, I know e to the infinity power is infinity, and infinity minus 1 is definitely infinity. Okay, so this is a form I can use L'Hopital's on. So we can use L'Hopital's or LH on this also. Okay, so this will be equal to, I'll write my LH above the equal sign to indicate I'm using L'Hopital's rule at this step. So equals the limit as x goes to infinity. And now I got to take the derivative of the top. So I need chain rule. The outside function is this 2 is this power that comes down. So I get 2 times, keep the inside the same, ln of x. Subtract 1 from the power, which makes the power 1, so I don't need to write it. And then I multiply by the derivative of the inside, the ln of x, which is 1 over x. Okay, that whole thing over the derivative of the bottom, and the derivative of e to this stuff is e to that stuff. But then I need chain rule and multiply by the derivative of that stuff, of the 2x, which is, that derivative is 2. Okay, and the derivative of minus 1 is 0, because that's a constant. Alrighty, so we have this. Let's simplify it a little bit. We get the limit as x goes to infinity. I can cancel the 2's, and then this will become ln of x over, I can bring this 1 over x. I can just bring the x to the denominator, and it becomes x e to the 2x. But make sure you see how I did that, how I got to this step. Alrighty, at this point, let's try plugging in again. Alright, so on the top, I get ln of infinity, which is infinity. On the bottom, I'll get infinity times e to the infinity, which is also infinity. So I get infinity on top, infinity on the bottom. Well, so let's use L'Hopital's again. Use LH again. This is still a form I can do L'Hopital's on. Okay, so I'll put equal sign. I'll put an LH above the equal sign because I'm using L'Hopital's now. So we have the limit as x goes to infinity. The derivative of the top is 1 over x. And on the bottom, we need product rule. So I'll get the first function times the derivative of the second, which we've already done actually earlier in the problem. It's e to the 2x times 2 times the derivative of the exponent. Okay, and then plus the second function, e to the 2x, times the derivative of the first, the x. That derivative is 1. All right, and now let's just try plugging in. If we do that on the top, I'll get 1 over infinity, which is 0. And on the bottom, I'll get infinity times e to the infinity times 2. That's going to be infinity. And then plus e to the infinity, which is infinity. So I'll get 0 all over infinity, which is 0. So that's my answer. So sometimes I have to do L'Hopital's rule more than once to be able to arrive at my answer. Okay, so I want to give one other general remark about problems like example 2, when we have these infinite limits, to get an intuitive sense for what the answer should be. So the remark is, in general, as x goes to infinity. And so the remark is going to sort of classify which functions grow more quickly as x goes to infinity. Okay, so it turns out log functions, I'm going to do 3 types of functions. Log functions, like x to a power functions, and then exponentials. Log functions, out of those 3, grow the slowest. So they're going to be less than things like when I have x to a power, or that power is some number that's bigger than 0. That doesn't have to be an integer. It doesn't just have to be like x squared or x to the 5. This could even be for like a root, like x to the 1/2 or x to the 1/3. Okay, and then, so these power functions, they will grow slowly, more slowly than exponential functions. And exponential functions. So using this remark, on our limit, we can get an intuitive sense for what the limit should have been. I have a log function on the top and an exponential on the bottom. And because x is going to infinity, we can use this general remark about growth, which says, oh, the exponentials are going to be growing a lot more quickly than the log function. So conceptually, because of that, the denominator is way, way, way bigger than the numerator is. And that's what's making the whole thing become really small. That's why the limit ended up being 0. So in our class, I can't just use that to say like, oh yeah, it's 0 because of this remark and show absolutely no work. I do want you to be able to show these steps to show how we get that answer. But this remark can give you a sense of, well, what should the answer be before you go to actually try it. So in terms of our goals for this section, we finished goal 1, applying L'Hopital's rule to evaluate limits of the form 0 over 0 or infinity over infinity.